Hey students, we're going to talk about buffers today, and we're going to start off with section 15.1. I've decided to try to follow very closely your textbook. So if you have your textbook, if you can grab it and take a look, because we're going to be going through some of the example questions. Okay, so section 15.1 deals with common ion effect. I'm going to keep this very, very simple. There's a lot more calculations in the textbook for it. But what common ion effect says is that if we have a weak acid in equilibrium, now I'm just going to do a more simple Arrhenius style for right now. So HA, weak acid, A minus its conjugate base. Okay, so we have the weak acid in equilibrium with its conjugate base. And if you look back in your notes, let's say, for example, this was acetic acid. And we did some calculations with a 0.1 molar solution. Look back in your notes. What we found is that it was 1.3% ionized. So that was with setting up our ice chart, finding Ka, checking our assumptions, if we could ignore X. I won't redo that whole problem because you can go back and take a look at that in your notes. But it had a certain percent ionization, which was 1.3% ionized. And what common ion effect says is that we can add a common ion. So for example, I'm going to switch colors here. We could add to this equilibrium something like sodium acetate. Okay, sodium acetate is, we're going to break it apart. It's aqueous, so sodium ion and acetate ion. And now we have a common ion, meaning we have acetate added. Don't forget our friend Le Chatelier's. What does he say is that if we have a system in equilibrium, so the weak acid in equilibrium with its conjugate base, and now we mess up that equilibrium by adding something, this will definitely shift away from the added acetate. Okay, and so it's going to shift left. I want you to think about for a second what that's going to do to the percent ionization. So what it will do is it will decrease. So a common ion will always decrease. The percent ionization of the acid. Does that make sense? Because it's going to shift it to the left. Okay. Now, your book is going to show you via calculations, it's going to prove this to you. I want to keep things simple with everything going on, so I won't show you the calcs. This is more conceptual discussion, that if we added sodium acetate, potassium acetate, lithium acetate, anything that introduces the acetate ion, that this equilibrium is going to shift left and the acid will not ionize as much. Okay, now that's going to be an important thing for us as we move forward, the concept part. Okay, so we're going to talk about buffers. And buffers, I can't think of a more important concept if those of you majoring in biochemistry and biology and in chemistry. So what we're going to do is we're really going to focus on the conceptual side and then also look at the calculations. And so let's first define what buffers are. They're going to contain a weak acid and its salt. So let me give you some examples. So our friend acetic acid, its conjugate base, and really that's implied in the salt, is really the conjugate base. So you'd have sodium acetate. Now that's the salt form. The salt has the sodium with it, but the conjugate base is just the acetate part. So when you're looking at these, you need to kind of, I would say, ignore sodium ion, understand that that's the salt form, sodium acetate, but it's really the conjugate base that we're going to be mostly concerned with. Okay. Another weak acid, HF, in a solution with potassium fluoride. That would be buffered. What is not buffered are solutions with strong acid and their conjugates. So not buffered would be like HCl with NaCl. That is not a buffer solution. Okay. The importance of a buffer is that they maintain pH. The solution will maintain the pH. It won't be perfect. It might fluctuate, but it'll maintain it when you add hydroxide ion, strong base, or protons, which would be our H plus strong acid. And this is going to be very essential in biology because you have experiments that require a pH to stay stable. And if the pH in an experiment changes too much, you could kill off whatever cells that you're working with. Now in chemistry, we might need a set pH as well for an experiment to run because there's going to be some processes that require the pH to stay around a certain value. And then what we're going to do at the end of this PowerPoint is talk once again about the bloodstream. And then I'll recommend to you or post up actually on Canvas, really interesting worksheet. It's not so much a worksheet, but it would be a handout regarding bloodstream pH. Okay, so I left this space here. So we're going to have a weak acid and its conjugate base. Those would be our buffers. And one thing I want to show you on this, since I gave you kind of the easier examples on the other side, would be that, let's say I'm looking at this phosphoric acid, very important biological acid. Its conjugate base is H2PO4 minus, one less proton. So this is one buffer system. That's a different buffer system from H2PO4 minus with its conjugate base, which is HPO42 minus. And then there's a third buffer system, which would be HPO4 2- and phosphate. So this is a third buffer. As we progress in this presentation, we'll talk about which ones would be used when. But I want you to realize that when you're looking at buffered solutions, it's going to be the weak acid and its conjugate. And remember, they vary by 1 less H+. So in other words, we'd never, ever talk about a buffer of H3PO4 and phosphate. That's not a thing. Okay, so this is from your textbook, Interactive Example 15.2. So hopefully you have your book in front of you. If not, it's okay, it's here. But so a buffer solution contains 0.5 molar acetic acid, and here's the Ka, and 0.5 molar sodium acetate. Take a minute and find the pKa of this solution. So negative log of that should have been 4.74. Okay, so I would just want to have that handy for, excuse me, later discussions. Okay, so let's take a look. 0.50 molar acetic acid and 0.50 molar sodium acetate. The first thing I want you to do is to identify who's who. The acetic acids are weak acid, HA, and the acetate is A-. So let's go ahead and highlight that right now. Okay, and now we want to know what's the pH. So we're going to set up our typical ice table. So this is going back to what you've been practicing so much of. And this is looking at what I just said, which we have our weak acid, which we'll call HA. Na+, either acid or base, that's just a spectator. Acetates are conjugate base, A-. And the water is present in the ionization equation, but we are concerned with the weak acids ionization for the pH. Okay, so let's set up our ice table. We're going to set up our equation for its ionization. Same thing we've been practicing over and over, and hopefully this is becoming very easy for you. Okay, but I want you to notice something's changed in our buffered solution. I'm going to go to a different color. How about purple? I have 0.50 molar of acetic acid, but in this case, with a buffer, we have acetate ion is also there. That is our common ion. It's present. And so let me finish the ice chart and let's talk about what that little fact about the common ion is going to do. So I'm going to show this as minus X plus X plus X. Okay, so the only thing that's changed, but it's a very, very important change, is what's changed is the fact that I have acetate ion present there from the beginning. So that's new, right? That's not something we've done before. And what is that going to do for us? Is it's going to really affect X. Because what we said with Le Chatelier's principle is that when a common ion is present, the equilibrium shifts back to the left. And what does that mean? It means that X is smaller than normal. X will be really small. Okay, so let's take a look. This is setting it up. See this part here? This is from the ice table above. Okay. Oh, I took up the space there. Hold up. Okay, so here was my ice table. Okay, I already wrote this out. So this is just our ice table. I already wrote this. Okay, X is super tiny. And then here, just like any other ice table, we're going to put it into the Ka expression. So once again, products over reactants. And we'll plug in our values. So we have X, 0.50 plus X, 0.50 minus X. Now here, this is the important part, because common ion effect means that it's going to shift the equilibrium back. X is very tiny. And this makes things so much easier, because then what we'll have is Ka will equal X times 0.50 divided by 0.50. And what do you notice about them, because the concentrations here are the same, is that they cancel. And X equals 1.8 times 10 to the negative 5. So if X equals that, then the pH is negative log of that will equal 4.74. Okay, so this is going to be our key concept number 1. Solutions, buffered solutions, where HA equals A minus, pH equals pKa. And if you have been working on your lab, we explored this concept in there as well. Okay, so buffered solutions where HA equals A minus, pH equals pKa. Okay, now what I want to show you, and this is going to be really important. Your book does introduce this. I think it introduces it a little late. But what's really important here is that we work buffer problems from our Ka expression. And that's fine. So you can do buffers by using your ice charts and then plugging in to Ka. However, there is a much easier approach to buffers. And what that approach is an algebraic rearrangement of the Ka expression, where we take the negative log of both sides and then do some algebra. Your book shows the derivation. And when you do that, we end up with a super famous equation in chemistry called the Henderson Hasselbach. And from that algebra comes the following form. pH equals pKa plus the log of A minus over HA. Now, what do I like about this one so much? It's so much easier to work buffer problems. Let me show you why. Because what it's really telling us is that the pH of our buffer is going to hover around the pKa. So buffer systems will work when it's around the pKa. We're going to come back to this at the end. Okay, but so we're going to quantify that a little bit more. And then the second thing that's so important is that the ratio of A minus to HA determines the pH of the buffer. And it's just so much clearer and spelled out in this version versus this version. This one is a lot, in my opinion, a lot easier. Now, I'm hoping that we can get to the point where we simplify it so much that we're not intimidated by this at all. So what do I mean by that? That we had a 0.5 molar HA and a 0.5 molar A minus, right? Acetic acid and acetate. Previous question, right? And when I look at this, if I understand common ion effect, okay, I'm going to write it back out, but I have 0.5 of this. I have 0.5 of that. X is really small, so just rewriting what we just saw a few minutes ago. But if I know X is very, very tiny, if I know the fact that we can cross out this X, then when I look up at this Henderson Hasselbach equation, I want you to notice what's going to happen is that I can do the following. I can say pH equals pKa. Where did I get that pKa? The Ka of acetic acid is 1.8 times 10 to the negative 5. So the pKa is 4.74. Negative log of that number. Now notice what's going to happen. I'm just going to do this, plus the log. Here's my A minus at equilibrium. Now, technically, it's plus X, right? But I'm going to switch that color to a different color because we can ignore that. Common ion effect says it's not going to ionize very much compared to that 0.5. So let's keep going. Oops, I didn't mean it. I meant to go back to the red. That's going to cancel too. Or cancel out, I should say, because it's so small compared to 0.5. And then to really show you what this means, This just simplifies to this. And notice what happens there. This cancels out. And the log of 1 essentially is 0. So pH equals pKa. Okay, now what I'm hoping that you do is that when you see a buffer problem like this guy with the concentration of weak acid and its conjugate, that you simply plug those in to Henderson Hasselbach, and then you're done. It makes it super easy. Okay, we're going to practice those when I see you in the Zoom office hours. I'm going to give you some to try from your textbook, and we can practice that more. Now let's talk about why buffers are important. Is their whole point is to resist changes in pH. Okay, so what does this mean? What it means is that, let's say we have a beaker and we have in there acetic acid and acetate. They're both in there, 0.5 molar. Okay, and we have 1 liter of the solution in this example. Okay, now let's picture what happens when we add sodium hydroxide. Okay, now NaOH in water will break apart into sodium ion and hydroxide. And now you're going to ask the question, what reacts with a strong base? So I'm going to come over here. I have an acid and I have a base. So the question's going to be, who's going to react with the strong base? And the answer is acids react with bases, period. You've never seen 2 bases react ever. So here is our answer, that acetic acid is going to react with the hydroxide. Now, if you want to write it as NaOH, that's fine. I'm going to highly recommend that when you see sodium ion, you just say spectator, forget about it, not deal with it. Okay, take a second to write what you're going to get when hydroxide reacts with acetic acid. It's going to be water and acetate. And what you're going to now see then is that acetic acid is reacting. So acetic acid is going to decrease in the buffer, and acetate is going to increase. So if you think about the ratio in Henderson Hasselbach, this ratio, it's going to change, right? You're going to increase A- and decrease HA. That's going to increase the pH. But it's going to be slight. Okay, so with this in mind, let's take a look at the calculations for this, but this is the concept. And I can't tell you enough that you need the concept. So once again, real quick, your buffer has both weak acid and conjugate base. If you add a strong base, hydroxide, strong base, the weak acid's going to neutralize it. But what's that going to do is it's going to decrease the amount of weak acid and increase the amount of conjugate base. So this ratio that's so important in the buffer system is going to increase, and the pH will rise, but it just won't be by a huge amount. And that's the part we're going to focus on. So this is going back through the ideas that I mentioned to you, that we have weak acid, sodium ion spectator, conjugate base, strong base, and then the water that's there. And the important reaction is bases and acids react to neutralize. So this amount of acetic acid is going to decrease, and the amount of acetate ion is going to increase. This reaction is super important to the calculations. Okay, now this chart here, it looks like an ice chart. It is to some extent, but I want to show you that the equation is the neutralization. So this is the neutralization we just talked about. The hydroxide reacting with the weak acid. Now, let's add in the numbers. The problem was, or the question was, that we had 0.5 molar acetic acid and 0.5 molar acetate in a buffer. And we had 1 liter of it. So you see here, this 0.50 moles, that's because molarity times volume in liters gives us moles. So we know how many moles are floating in there. 0.50 times 1 liter is 0.50 moles. Notice that's the same for both of these, because that was what our question was. Okay, I want to highlight something very critical here. The amount of hydroxide that's been added is 0.010 moles. That was part of the question, right? This was part of the problem. Okay, now what's going to happen? That's going to get neutralized. And I want you to notice one other very important thing. The 0.010 moles is less than 0.50, right? You see how this is a lot smaller than this. Okay, that's really, really critical, because the buffer can only handle a certain amount of strong base. And then the stoichiometry. So this is, now we're back on 200 footing, Chem 200 footing. The 0.010 moles is neutralized. And it's neutralized completely because it's the limiting reagent. And I put LR for limiting reagent. So let's think about, if I start off with 0.50 moles of weak acid and 0.010 moles of strong base is neutralized, you're going to end up with 0.49 moles of weak acid. The strong base is completely neutralized because that's the limiting reagent. And then you're going to make 0.010 moles. So you're going to end up with 0.51 of the base because you started with 0.5 and you're going to add on an additional 0.010. Okay, now I know what's going to happen when I click. We're going to see a new ice chart and we're going to see all sorts of things. But what I want to show you is that the fastest way to end this is to just say pH equals pKa. That's the pKa of acetic acid. And now I'm just going to plug in my new numbers. The base is 0.51 and the acid is 0.49. In my mind, I can think that there's an ice chart and there's a plus X, minus X, but I don't really need it because X is very small in the weak acid ionization. So I can just finish up this problem right here. Okay, we'll come back to this idea. This would be our shortcut. Okay, all right, so let's take a look. Okay, now what this is showing us is what I call the long route. And it's good conceptually to know it. Here was my weak acid after the stoichiometry. So this was after the stoichiometry. This was the acetate after the stoichiometry. Then it ionizes, but remember, X is tiny due to common ion. And then once we have this all set up, you can plug into the Ka expression. So here's X times 0.51 plus X, 0.49 minus X. We ignore X because common ion is going to tell us that it's very small ionization. X will equal 1.7 times 10 to the negative 5. And then let's see what pH that gives us. Gives us a pH of 4.76. Now, originally, when they were equal, the pH for when they were equal was 4.74. So if you notice, the pH did go up. The pH did increase. By a small amount. If you notice, it's because you have more base and less weak acid. But it's not by a large amount. So the buffer maintains the pH around its pKa. Now, what I would suggest to you, though, is that it would have been faster to just plug in to Henderson Hasselbach. Okay, and what we're seeing here, let's kind of do a little bit of a comparison. From that previous initial question we did, where HA and A minus were equal, pH equaled pKa. But now we've added 0.01 moles of hydroxide. The pH is now 4.76. Why? because A minus over HA is now greater than 1. So this number here, that ratio has increased, so the pH increased. Okay, and I'm going to give you a homework one that we can do via Zoom. We'll practice this idea again, and I'll try to pick one that's adding H+, so we can see what happens if we add strong acid instead of strong base. But this ratio is critical. Now, the other thing I want you to realize is that buffers then are only going to work around a pKa, a pH that's around the pKa. So if we look at this idea, and we'll come back to it again, is this particular buffer system is going to hover around a pH of 7.4, and more specifically, the pHs that this buffer is going to be useful for are pHs that are plus or minus 1 unit from the pKa. I'm going to introduce that now, and then we'll keep talking about it in later presentations. But acetic acid with acetate is really only going to work around a pH of 4.74, but more specifically, a pH value of 3.74 through 5.74 for an acetic acid acetate buffer. Okay, so what this is showing is that the original solution where A minus equaled HA was the pH equaled the pKa, but we added 0.010 moles of hydroxide and it went up to 4.76. So there was a change. For sure the pH is going to go up when we added strong base, but it didn't go up by very much. If you were to drop this amount, 0.010 moles of hydroxide in 1 liter of water, pure water, and you were to do the math on that, so where hydroxide ion was 0.010 molar, let's think about what the pH would end up at. So our POH would be 2. And then the pH would be 14 minus 2. This is fine, but my brain doesn't like this other way of doing it. I like this route better. Just, I think, easier. Okay, so if you were to drop that amount of hydroxide in pure water, the pH would end up being 12. And whatever experiment you're doing has now been killed off. Like your cells aren't going to work, the reaction's not going to work. So that's a huge and significant jump, right? That's really, really a great calculation to show why buffers are important. Okay. All right. That's a +5 pH difference. Okay, so for those of you that like graphics, whenever you have a buffer calculation. It says, hey, my buffer's at a certain pH. What happens when we add H plus and hydroxide? The first thing you're always going to do is stoichiometry. Your strong acid and base will be limiting reagent. And then you do an equilibrium calculation. But can I add instead in here that I would like you to think about using Henderson Hasselbach? Now, my students previous to this, whenever I say Hasselbach, they think I'm saying Hasselhoff, so that they've been calling this in previous classes like the Baywatch equation. But that's fine. But I just think it's so much easier to use Henderson Hasselbach versus using the Ka expression. So there's always work involved in finding the pH after you've added H plus or hydroxide. Okay, so the important equation when we're talking about how buffers work is that the weak acid will neutralize strong base. And what we'll see is we increase A minus and decrease HA. So A minus over HA is greater than 1, and we see a slight increase in the pH from pKa. Okay, that's the one we did. So we did that calculation. Okay, and let me see these slides here, sorry. I'm not sure I really like those graphics, so I'll skip those. So here is the idea that Henderson Hasselbach is so helpful because it's this ratio of A minus to HA. This ratio determines the pH. Can you tell that I really love Henderson Hasselbach? I'm such a nerd, but it's like the best equation. It just makes our life so much easier. And what it will do for us is that we can just plug directly into that equation after we figure out what's going on in the buffer. Okay, but if A minus to HA increases is greater than 1, pH is greater than pKa. Meaning, think about it. You have more base, right? More base makes the pH basic compared to pKa. When you have A minus over HA less than 1, then the pH is less than pKa. And your buffer is more acidic. And then when A minus equals HA, where should I put that one? pH equals pKa. Okay, and that's going to be conceptually something for sure that I'm going to ask you, is that idea. And so the other piece that's so critical is that when you pick buffer components, if you want to preserve a pH at a certain pH point, you have to pick a buffer whose pKa is near that pH you want. So remember, for buffers then, the pH that it's going to guard is going to be always plus or minus 1 unit from the pKa. Okay, so I know we're getting a little tired of the video probably. I find that I get a little more tired talking to a computer than when I'm in front of a class for some reason. So let's just finish this off before I run out of gas. Okay, first thing we're going to do, HF, 2 molar weak acid. That's our HA. F minus is A minus, conjugate base. Forget the sodium ion. The long route would be to write the ice chart. The simple route will just be pH equals pKa plus the log of F minus over HF. Now, I need to grab my book. So if you have your book, let's go to the back. And I don't remember, well, I think it's 6.8 times 10 to the 4, but maybe I'm wrong. So let's go back to your back of your book. See if we can find the KAs. Should be a table in this thing. I'm not as familiar with your book as I was the other textbook. Okay, so I'm on appendix A. It says A24, appendix A5.1. So hydrofluoric acids, Ka is 7.2 times 10 to the negative 4. And I don't have my calculator. Wow, oh no, I do. So I'm going to find the pKa, negative log of that. .14. So I'm ready to go. pH equals pKa plus the log. And I'm just going to plug in directly. Yes, there's an ice chart. Technically, this is a plus X minus X, but those are very small. So pH, in this case, equals pKa. And that's because they're the same concentration. And the ratio is 1 of F minus over HF. Now, I know it didn't ask this, but HF and F minus will work in a buffer range of 2.14 through 4.14. That's where it's going to work. So pH that this is useful for is plus or minus 1 unit of pKa. Okay, the other thing that your book didn't really mention, but is very critical, and I think it's coming up in the next section, is that buffers are going to be really important to set them up so that you have higher concentrations of weak acid and conjugate base, because then they can neutralize more additional strong acid and base. So these numbers are better when they're higher. If they're tiny, they're not going to be as useful for buffering capacity, but I believe that's 15.3, so I'll talk about that for the next section. Okay, so what's the pH of the solution? If 0.020 moles of strong acid is added to, and we're going to say 1 liter of solution. Okay, so let's picture I have HF and F minus. Who's going to react with H plus? Do acids react with acids? No, absolutely not. So the F minus is going to be the species in there that's going to react with H plus. Okay, so this is our important equation. Oops. So that's our important equation. So now we're thinking, yay, stoichiometry. So remember that graphic, it said do stoichiometry first, and then Henderson Hasselbach and equilibrium second. So from the previous one, we had 2 molar F minus, and we have 1 liter. So that's 2 moles. And we had 2 molar HF and 1 liter. So that's 2 moles. And then we're adding, I'll put it in a different color if you want. Okay, this will always be our limiting reagent or we're going to kill the buffer. So that's going to be completely reacted. And that's the amount. That should be 1.8 and 2.2. Oh, 1.98, excuse me. Yeah. Sorry. This is where I get tired, remember? Okay, and now I'm going to say pH equals pKa. Would you believe I forgot what the pKa was already? .14 plus the log. Now, even though my neutralization equation has the F minus over here, that's still our base. So that 1.98 goes on the top, right? That's our base. And the 2.02 goes on the bottom. So let's see what we get. Going to barely change. 3.13. So our buffer did a good job. Okay, it went down because we added H plus, right? But not by a lot. The other thing I want to show you is how important it is that the 2.0, like these are a little bit bigger concentrations because the solution can resist more strong acid being added, okay, than if it was less concentrated. Okay, now let me just show you what I mean by that. It'll take you a minute to take a look at that. Okay, now, what if I did this? What if my buffer wasn't so concentrated and it was a 0.020 molar or moles to begin with? Now, do you see how that's not going to be a helpful buffer? Because what would happen is when we add that amount of strong acid, we completely destroy the buffer. That's not helpful. So what's really important in buffers is to make sure that we start off with a high amount relative, high number of moles of weak acid and conjugate base. That's going to help. And we'll talk about that more in the next section.